Okay, so today we're going to talk about level populations, and we're going to pick up where we left off. I'm going to go through the homework first so that we talk about all the stuff that you just spent some time doing. This homework set seemed to go pretty smoothly for everybody, but here is your opportunity to speak up and holler if there's anything that you want to talk about. So I'm going to go kind of quick, and I'm not going to do all the derivations unless there's a particular part of a derivation that you want to see. Okay, so this is homework 2. So the first problem was prove virial theorem. So the way I do it is I start with the moment of inertia. I equals the sum on mi ri squared. I take two derivatives, and then I turn the stuff that I get out of that into kinetic energy and potential energy. I'm not going to go through all the detail because I've done that already. Does anybody have any questions on that? On how to go through that process? I think everybody got that just fine. So the first one was to prove it, and the second one was we have this thing, I double dot. What kind of averages can I take over this thing so that it goes away? And then I'm left with just 2ke plus pe, or u or whatever, equals 0. When can I say that? Well, if the orbit is closed, that means that when I integrate I double dot, I'm left with the integral of a full derivative evaluated at the endpoints, which is just fundamental theorem of calculus. And if the endpoints are the same point, then I get 0. So integrating a full derivative around a circle gives you 0. So if the orbits are closed, like planets going around the sun, or if it's statistically relaxed. And what do I mean by statistically relaxed? I mean simply that you can say that I double dot is 0, so it's kind of tautological. But really, if something is sitting there for 1,000,000 years, you can assume it's relaxed and yeah, not a million isn't very long, but 1 billion. Go on.
When proving the virial theorem, did you want us to show each step of why summation of Ri Fi is equal to U?
I wanted to see most of that. But
like from what was like the nasty math that's put on the board. Oh, okay.
There's some gnarly math. I'd like to see most of that if you can.
Okay.
So okay, I gave in there. There's a PDF under files that has my derivation of virial, and that goes through all of the gnarly stuff. And in there, I present that second part 2 ways. So the potential energy, you get a term that looks like mi ri double dot, and you got to do a little work to make this times ri. There's an ri there. That ri is important. So the cheesy way to do this is to say mi ri is just the force. So this is just gmm over r squared times r, and the r's cancel and you're left with potential energy, which is a little cheesy.
Could we have done that?
If you do it this way on the final or on the midterm, I will probably take a point off and saying it doesn't actually work that way, but it works pretty good, so that's fine. I might take off like half a point. So going through all that math is maybe worth half a point on the midterm. The long way to do it is better, but it gets you the same basic idea. So, wave hands when it's appropriate, and then stop waving when it stops being appropriate. That's how you be a physicist. Yeah.
Is it worth, if we realize we didn't do as much as you might have wanted for the homework, that we go back and do it and resubmit it, or do we just?
Ask me. Ask me point by point. Like, if there's one that you want to resubmit, just drop me a line and say I want to redo this one, and that's probably fine. But so his question was, if I hated the way I did one, can I redo it? And the answer is basically yes, but please let me know beforehand, because I'm not always going to go look back and pick up late assignments that got resubmitted after I grade them. So, but yeah, go ahead. That was the long answer for yes. Okay, So proving virial, we love virial. It comes up all the time. We do a lot of astrophysics with it. So the second one I want to spend actually a little bit more time on. So here we're talking about delta Sco. So in a constellation, so constellations are very cool because they're ways that we can kind of find our way around the sky, because hey, this bunch of stars kind of looks like a fish, and this bunch of stars over here kind of looks like a dude holding a sword, and these two stars look like a ship that's being attacked by a kraken or whatever. So the constellations are useful for finding our way around the sky. They're not useful for determining what kind of birthday you're going to have or really any other aspect of your life. So the constellations are merely where we perceive the stars, but they're very useful for finding our way around. So we like to label the stars in each constellation by which one's brightest. Alpha is brightest. Anybody want to guess which one's second brightest? Beta, and then delta, right? So it's pretty straightforward. So Alpha Centauri is the brightest star in the Centaurus. Delta Sco is the fourth brightest star in Scorpius. Okay, so what I gave you was I gave you the temperature is 27,000 Kelvin, and the radius is 4.7 times 10 to the 9 meters. And the star, and I gave you the distance here, is 136 parsecs. Not sure why I had to look at the units. There's not going to be anything else. Okay, so then I asked for several things. So I asked for the luminosity, the absolute brightness, the apparent brightness, the distance modulus, the flux at Earth, the flux of this. Oh, I'm sorry. I asked for the flux of the star, the flux at Earth, and the peak wavelength. Okay, before I start going through any details, are there any one of these that anybody wants to actually talk about in particular? Make sure, yeah.
So I think in the notes for at least one of the slides on the slick slides, it had distance modulus written wrong. It had it written as a negative.
Oh yeah, I wrote it as big M minus little m somewhere in the notes, isn't it?
I think so, yeah.
Yeah, I apologize for that. I realized that this morning when I was grading.
So
I was
didn't
oh, that says big M minus little m in the notes, doesn't it?
It said it in like 2 slides in a row, and then the very next slide it said it correctly.
It's
like on the
entirely possible.
list of things where it was like things that look like the fluxes. On that one it was wrong. It said like -5.
If you could email me that'd be great. Details in the slides, you should always, if you ever have a question in the slides, there's typos in the slides, and I make those all the time. So yes, distance modulus was wrong by a sign.
Can you do 2, 3, and 4?
Yeah, I'll go through them all in detail. But I just
2,
wanted.
3, and 4 because we got way too bright.
I know you got weird numbers, didn't you?
We got very bright.
I know why. I ran into the same thing when I sat down to do this problem. I was like, I am off by, because what do you get? What's the magnitude on the Wikipedia page? It says.
Hold on.
For the apparent one, we got.
No, let's talk about the absolute.
Absolute. Oh, I have no. What I got was -6.
Yeah.
Yeah, so you get -6.
Yeah, we got around -6, but on the.
Let me erase this V real quick, and I'm going to write -6.4. So MV is a much different number. The difference is because what you computed was the bolometric magnitude. That's all of the light. But what's on the Wikipedia page is the visual magnitude,
Oh my god.
which is less.
So if we could see all of the wavelengths, we would see it way brighter in the night. Okay. Oh.
Which is why we compute the peak wavelength, because the peak wavelength is 100 nanometers, which is way too short to see. You can see to about 400 nanometers.
That makes sense.
So if you think about this as a black body, so this is wavelength and this is the flux. Here's visual. So this is what I can see. This is from about 400 nanometers to about 700 nanometers. So the sun looks like this. So the bulk of the light is in this visual. But Delta SCO is a big old star. And it looks like that. Oh, pardon me. That's terrible. These should never cross. Black bodies don't cross. It's very important that they don't cross.
What if they do?
Then you've broken something. If black bodies crossed, we wouldn't be able to learn anything about the universe. It would be real problematic. There's a lot of physics that kind of we take for granted for black bodies being well behaved. So the flux, like the bulk of the flux, is down here in the ultraviolet. So let us go through. But I'm not gonna lie, I was stuck for like 5 minutes on that one. I was like, damn it, why am I getting the wrong number? And I just sat and stared
So
at
the
it.
right number there's asked for is the bolometric, which is like negative 6 point.
Which is negative
I got
6.
Yeah, so we got the right
6.489.
numbers, it's just they were, okay.
You did the right thing, and then, so I appreciate, was that?
That's why they didn't line up.
Yeah, with what you were seeing elsewhere. Cause you gotta look up the right thing.
But would the distance modulus still work?
Yeah, you get, if you use my distance modulus, you get 1 over the number. Cause it's off by a factor of 10. You're gonna get micrometers. You'll get angstroms if you do it my way instead of kiloparsecs. Well, let's go through it and see.
I got negative 8.5.
I can't see what you did from here, so I'll look at your stuff. I haven't gone through and graded everybody's stuff, but as long as you did basically what I did, and you screw up putting numbers in the calculator, then I don't really care. I don't care about numbers, to be honest. What's that? I just care about the process. That's all I care about. I care about numbers and shapes and relationships. Okay, so let us go through. So the luminosity, how do we compute the luminosity? Where's my, oh no, they're not on that page. Yeah. So the luminosity, so we model stars as a black body plus an atmosphere. Generally, the atmosphere we can ignore for the bulk of the light because it doesn't produce any light. It just kind of gets in the way. So if we treat Delta SCO like a black body, then the luminosity is just given by Stefan Boltzmann, which is just 4 pi times the radius of the star squared times this number, which you look up, times the temperature to the 4th. Does that make sense? So what would happen if the star suddenly increased by a factor of 2 in radius but kept the same temperature? What would its luminosity do?
Increased by
Increased by 4.
Increased by 4. So both radius and temperature matter. When we get to the HR diagram, this will become apparent why this matters, because things get real bright even though they're dying because they get real big. So you plug in 27,000 into here and the radius into here, and this number you look up and you get 1.16 times 10 to the 31 watts, or something slightly different in ergs.
8.365, 10 to the 37 ergs per second.
37?
38.
Oh, okay. It's watts versus joules, or ergs versus watts. I should know off the top of my head. I only wrote down one of them. The front number should be the same because they're only different by factors of 10. But you should get a slightly larger number in watts, or in ergs. But I'll go through in detail. If you plugged in this and you didn't get that, then either you used ergs or you used type something else in.
I got something like barely slightly less than that.
I got
Like barely.
What'd you plug in for this?
That
What'd you plug in for this?
R?
Yeah.
What was written?
What'd you plug in for sigma SB?
the one we looked up.
Did you make sure
5.6?
sigma and R both use centimeters?
I printed 5.6.
No, I mentioned units.
I'll go through everybody's calculator work. As long as you plugged in something that looks like this and you plugged in numbers that look like that, if we got slightly different numbers, I'm not super concerned. Yeah.
Mine was like 8.183 times 10 to the 31st.
Times 10 to the what?
Times 10 to the 31st.
Oh yeah, that's fine.
It's the same power.
I mean, as long as you're in the right ballpark, I'll go look and see where your factors of 2 dropped off. But I'm not really concerned about factors of 2. What I'm concerned about is whether or not we're all
Ergs per second should be bigger though?
yeah
Okay.
by like 7 orders of magnitude.
Yeah.
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 Initially it was like times 10 to
I
the
haven't- I didn't
68,
use
which
Earth.
was
I didn't use it.
very, very wrong.
That's a little large.
Yeah.
In watts, that's large. Okay,
Everything he had to.
absolute volumetric magnitude, how do we get that?
Yeah,
Same thing.
too.
So in the last 7 words is larger because. But we don't like 1.0.
So the volumetric magnitude is minus 2.5 times the log base 10 of the luminosity divided by the fiducial luminosity, which is in the notes. Every time I teach a class, I'm like, man, I wouldn't write the book this way, I would do it different. And the book doesn't do it this way, which I think they should. So it's not in the book, but it's in the notes. There's other ways you can look it up as well. And I get a volumetric magnitude of minus 6.4, which I think is what everybody else got, which is a lot brighter, a lot smaller number than I think you get. I think the visual is the minus 1.
Okay.
I can't remember exactly. I should have written that down. But does everybody have any questions on using that to get the absolute magnitude?
How do we make sure that our L naught is like always the same? How do we agree on the same L naught?
You and I,
Yes.
it's in the notes. Use that number.
And that was 3.0123
Times 10 to the 38,
30.
I think.
28.
28.
Yeah.
I'm looking at
If in, this is the kind of thing that I would hand you on the final. So there will be a couple of numbers that I'll give you on the final, like like parsecs and AU, and this number, and G. So I'll hand you some of those things. Okay. Little m. Little m. And this was, as I was flipping through, I got to the first person's thing and it was like a little m minus big M. I wrote it wrong, didn't I? Little m, so the distance modulus mu is little m minus big M equals 5 times the log base 10 of d over 10 parsecs. So the distance modulus, which I asked for, I asked for first. The distance modulus, so I asked the question backwards. The distance modulus mu is little m minus big M, which is, what do you get, minus 5.6. Oh no, sorry, I'm reading this thing backwards. I asked for the apparent magnitude. The apparent magnitude, little m, is big M. You just solve that to the other side. Big M plus 5 times the log base 10 of d over 10 parsecs. And you should get 5.6. Stick on the wood. And then, oh no, not 5.6.
No, that's the.
It's minus 0.8, minus 0.8. It's just a stack of numbers.
It's just modulus, positive.
So it's minus 0.8, was that?
You said the distance modulus.
Yeah, I said the distance modulus, but I meant to read that, the absolute magnitude, which is 0.8. The distance modulus is just the difference of these things is 5. Then the flux, let's see, at the star's surface, you should get a very large number. And flux is just luminosity over 4 pi d squared. So at the star's surface, you should get something like 3.5 times 10 to the 10 watts per meter squared. And at the Earth's surface, you should get something like 1. Something that's like 5.2 times 10 to the minus 8 watts per meter squared. So something on the order of 10 and something on the order of minus 8. And then the peak wavelength is just 2.9 millimeters over the temperature in Kelvin. And you get 103 nanometers, which is much smaller than the visual. Okay, does that make sense to everybody? So this problem kind of underpins like a huge fraction of the astronomer's toolbox. Make sure you grok how all of these pieces fit together, and other variations I might make on these. Like I might give you little m and big M, and ask you for the distance. Okay. Veen and Rayleigh jeans. So I wanted you to put your hands on the Veen and the Rayleigh jeans limit, and I think people struggle with this one a little bit. V nu of t equals 2hc squared lambda to the minus 5, e to the minus hc over lambda kt minus plus 1, minus 1. And sometimes there's a plus 1 in the bottom and sometimes there's a minus 1, and they mean the opposite things. You get a minus 1 if you have Fermi-Dirac statistics, and you'll learn about that. Maybe in modern, definitely in StatMech. Okay, so the first thing we do is we look at the lambda small. So lambda being small means lambda is small compared to the other dimensionless quantities that it shows up with. And so that's really this business up here in the exponent. So for lambda small, we need hc over lambda kt, that's in the denominator, to be much, much larger than 1. That make sense? So if this quantity is bigger than 1, oh.
If the whole thing.
Raise all that to -1.
Yeah.
Dirt been the night away. So this becomes very large, right? When this is larger than 1, and then we can just get rid of this 1, and we're left with 2hc squared lambda to the minus 5, e to the minus 8, e to the hc over lambda kt. Not minus. That throws me off sometimes. And then the second, we say e to the hc over lambda kt. We take the Taylor series of this. This is 1 plus hc over lambda kt plus other things, plus that thing squared, plus 1/2, plus blah, 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 plus other things. And if I plug this into here, this 1 and this minus 1 cancel, and I'm left with 2hc squared lambda to the minus 5 over hc over lambda kt, and when lambda cancels that lambda, and I'm left with 2c, my h goes away. That's kind of handy that the h cancels out. It's rare that it does that. 2c kt lambda minus 4. So one of the things that you're allowed to do as a physicist is throw stuff out kind of willy-nilly, as long as you can justify it well enough. And that's what we do here. So you can do a full Taylor series of the whole thing. So remember, the Taylor series says f of x is f of x naught plus the sum on all the derivatives, 1 over n factorial f n of x at x naught. So you can do this for the whole function, or you can just do it for parts and say, well, this part's gonna blow up. It takes a little practice, but. So anyway, so here we have the Veen and Rayleigh jeans limits of the black body. Anybody have any questions on those? Pretty straightforward.
So that was number 4, right?
Yeah.
And that's
Yes.
all
Why was e to the positive hc over in number 1 of this? Why was it to the positive hc over lambda kt?
When it's
Shouldn't
still
No,
negative
it was
denominator.
negative.
I thought you crossed the negative out.
In the black body,
When you got to the end to the Wien limit, you said it was times e to the positive hc over lambda kt instead of negative.
because I made a mistake. because it's on the bottom, because I forgot that that was on the bottom. So that should have been a minus sign there. Sorry.
So wouldn't that case it go to 0?
Oh yeah, everything goes to 0, but we want to stop before it gets to 0. So when you're taking limits, you want to stop before everything gets to 0.
Oh.
Which is something that a lot of people said. A lot of people were like, and then everything goes to 0. I'm gonna just look at what you did right before that. Because you can send all your limits to 0 and then you have 0 equals 0, which is true, but not actually interesting. What you want is tiny thing equals other tiny thing, and then you want that to be actually factual.
Which equals 0.
Which isn't 0, which is a photon, which is almost 0, but enough to be problematic.
Which approximates to 0.
No, a photon's never 0. That's the beautiful thing, is we have these things that are so small, but not actually 0. Okay, compute the Lyman alpha transition in neutral hydrogen. So here we've got neutral hydrogen. Neutral hydrogen has this level structure. En equals minus 13.6 eV times 1 over n times n to the minus 2. There you go. So this is the energy level of the nth level. So if I want to know what the frequency of a Lyman alpha photon is, well, I need to know what Lyman alpha transition is. So the Lyman alpha transition is the ground state. Hydrogen alpha is the second one up. I'll talk about hydrogen alpha a lot because we really like it. It's a beautiful color and it's also incredibly useful. But Lyman alpha is the ground state transition. So this goes from 3 to 2. So what I asked for is the wavelength for a photon. What we know about wavelengths for photons is that they come from the energy. We know that E equals h nu, or E equals hc over lambda. This is one of the few things that I can remember is E equals h nu, and I have to get everything from that. So E equals hc over lambda, so we get lambda over here, and we're left with lambda equals hc over E, which is hc over the energy from going from this state to this state, which is minus 13.6 eV times 1 over 2 squared minus 1 over 1 squared.
So is it from 3 to 2 or from 2 to 1?
2 to 1.
Oh.
I said the wrong thing like 4 seconds ago.
Yeah, I was very confused
Sorry.
because you were like 3 to 2, and I'm like, what?
Because I'm looking at H alpha and I sometimes think about H alpha. It's the 2 to 1 transition. It's the ground state transition from the second state to the first state.
Is it fine if we use the Wright-Blur equation from like modern?
If it looks like this, yeah.
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 It's just simplified the HC divided by 13.6.
Oh, sure. Yeah. Yeah, so you just need, so then you should get 1216 angstroms. Or that's 121 nanometers. I'm not sure why the numbers all stick in my head in angstroms, but that's the ones that I remember. Okay, Andromeda, we'll do the last couple. One I'll do real quick, and one so Andromeda's really fast. So Andromeda has an apparent magnitude, MV of plus 3.58, and an absolute magnitude of minus 20.62. What's its distance? So that's easy. No, it isn't. It's easy once you've done it a couple of times. D equals 10 to the mu over 5
Plus 1.
plus 1.
Yeah.
Unless you want to multiply by 10 somewhere.
Plus 1? Where does the 1 come from?
It's
Another 10.
10 times 10.
Yeah,
times
okay, so the distance modulus is 5 log 10 d in 10 parsecs. Or 5 log 10 of d in parsecs plus 5.
Oh, is it fine if we multiply it by 10 before the 10?
Yes.
Okay.
The same.
That's why I stopped there for a second when I was like, where do I put that? I'm going to put it up here for now. So you get a +1 up here, or you need to remember that it's in 10 parsecs. That's how I did it when I was working out the equation sheet. I got 60,000 parsecs, and I'm like, wait, what the hell? It's not 60,000. Oh, right, +1. So you gotta just remember that the distance modulus has 10 parsecs in it, so you need this 5. And you get a distance of 600,000 parsecs, which is actually low. The actual distance is bigger than that because of visual extinction, which I did not talk about, but I might talk about later.
It's like,
So that's a
Was that?
it was like 690,000 or something.
Yeah,
right?
yeah.
So like 700,000.
Yeah, but it's like 750,000. You get 692 kiloparsecs.
Yeah. Okay. You wrote 600, so it was rounded down. So I was like,
Yeah,
I rounded
yeah.
up to 700, so that's why I was confused.
That's all right. So it's closer to like 780 because there's actually a lot of dust in the way that makes it look further away than it is. But yeah.
Can we get a, I know this is a bit of a tangent, how can we get an absolute magnitude of something that isn't not a single object, but like an aggregate of stars? Like a galaxy?
You mean, what does that mean?
Yeah, like for, I mean, I get that it means the same thing, but like, can we just like average the entire, like a bunch of black bodies into one black body?
And then you would have an average distance.
Or is that not using the volumetric magnitude? It's just like
Let me.
visual.
Yeah. So if you wanted to actually measure the absolute magnitude, you would measure all of the stars, but really the galaxy is not very big, so you just point it, you just put the whole thing on one pixel and just measure what you get. You just let the camera do the integrating for you. If you wanted to compute it from first principles, which is a thing that I'm trying to do with a grad student, you would make your galaxy model, you would put in all your stars. Each star is a little black body plus an atmosphere, so you would add up all of those black bodies and all of those atmospheres, and you would get the total light. So that's a really good question. So M is going to be minus 2.5 times the log base 10 of L over 4 pi d squared. So to get L is going to be the integral of all the light. So you just add up all the stuff, and then that's your luminosity. That's your luminosity. Oh, I'm sorry, not 4 pi d squared. Oh, not. Wrong one.
I'm still using Vega.
Yeah, it's cool. Okay, and then the last thing is prove Stefan Boltzmann. And that one, I'm not gonna go through in horrible detail just because watching me do calculus is boring and I screw it up all the time, so it's confusing. But I'll tell you which bits was that?
That would be helpful to walk us through the.
Do you want to see it?
Kind of.
Okay.
At least the first sequence. Just any.
Do I have everything that I need to do it? Yeah, okay, so the black body is 2hc squared lambda to the minus 5 times e to the h c over lambda kt minus 1 to the minus 1. And this is in watts per lambda per area per solid angle. So centimeters, angstroms, steradians, if you like those. So what we need to do is we need to integrate over area, and we need to integrate over solid angle first, and then we integrate over wavelength, and that's the integral that's ugly, and you need this other integral that I gave you, 0 to infinity of x cubed over e to the x minus 1 equal dx equals pi over 15 fourth, pi the fourth over 15. So you can see that we're going to have some ugly integral that's just going to turn into a number, and that's fine. So there's 3 steps. Let's do the solid angle first. And then we'll do, actually let's do surface area first because it's dumb. And then we'll do solid angle. because it's really confusing. And then we'll do wavelength. Because it's where I'm certainly going to drop a 4. Was that?
That's exactly what I did like 3 times. I dropped a 4 and then I dropped a pi and then I was off by literally just pi. Like I had pi to the 4th when it should be pi to the 5th. And I was like, well, clearly I did the whole thing wrong. And then I realized, no, that's right there.
One of my clearest memories in grad school was sitting out on this porch where I used to take breaks and have smoke breaks with my buddy Mike. And I said to him after we were working on some physics problem, I was like, Jesus Christ, a career in physics is constantly chasing down a factor of 2. And I said this when I was in college sometime in the 90s, and it is one of the most accurate things I've ever said. I've been doing this now for a long time, and I spend all my time tracking down factors of 2 pi somewhere. So okay. So this one just gets you a 4 pi. This one just gets you a pi, not even that. And this one gets you all of the rest of the physics. So okay, let's go do it kind of slow. So the first thing we're going to do is integrate over surface area. So we're going to integrate b of nu of t d a. And what is the surface area element? We're in spherical coordinates. So now we got to draw this thing. So here's my octant of a sphere, and I've got theta comes down from here. Phi opens up from here. This is r. And then a little volume, if I'm going to draw a bunch of r's, they're going to be separated by d theta and d phi. We get a little box. The little volume element, dv, is r squared sine theta, dr, d phi, d theta. Okay, so this is what a volume element is in my universe. But we're at a fixed radius, so dA is the same thing. R squared sine theta, dr, d phi, d theta. But this r is fixed now. I'm not integrating over it. And I don't have a dr anymore because we're not integrating an r. This is just a d theta. And I integrate, so this integral goes from 0 to pi d theta. So theta is the one that comes down from the top. It goes from 0 to pi. 0 to 2 pi d phi times sine theta, and then b nu of t. And and an r squared. R for the star squared. So when I do this integral, the integral over the sine gives me a 2, and the integral over this gives me a 2 pi. So this whole integral just gives me 4 pi r squared times b nu of t. So that's just the surface area integral. So surface area integral gives us 4 pi r squared b nu of t. Then we got to integrate over solid angle, and this one's gross.
Doing that integral, did we have to say that weird stuff of the sine and the phi, or could we just say the surface area of a sphere? Like we just do the integral of dA, and then that just gives us an a times b nu, and then a is 4 pi r squared.
That's a very difficult question, because what your question is how are you going to grade? I don't really know how I'm going to grade everything yet. Because that's really it. This doesn't depend on surface area at all. So I don't actually have to do much of an integral. All I really have to do is multiply by the area.
Yeah, okay.
So if that's good enough, that's cool. But I also would like it if you know how to get the surface area of a sphere using calculus.
Gotcha.
So you can know both things. So so that's a really good question. Part of this class, like this is an astrophysics class, so that's really what I care about. But also, physics is all calculus. So make sure that you understand how to get the surface area of a sphere from calculus. But as a physicist and as somebody who's grading and as somebody who does problems, when I get to a place where I'm like, oh, I just have to multiply by the area here and I know what that is, I'm done. It's totally acceptable. I'm not sure how I'm gonna grade this.
But know that.
Yeah, so know both of those things because there's more than one thing that we're learning. The solid angle integral, we have a similar thing. We've got theta, phi, and now we're integrating over the whole solid angle. The only difference is we pick up an extra sign. So we have now this thing, which I'm going to call I2, whatever this crap is. We're going to integrate this over the same angles. We don't need an r squared now because I'm not looking at the surface area. I'm just looking at the angles, so there's no more r squared. I still get a sine theta d phi d theta, but then I also get a cosine theta for the projection because the photons are coming at an oblique angle. I don't get as many of those photons because they're spread out. So I get a cosine theta, and then this is the same angle components that I had before. So this integral d theta goes from 0 to pi, d phi goes from 0 to 2 pi.
It's not pi over 2 for theta?
Yes, theta's pi over 2 because you only go down to the surface. Thank you. As I was writing that, I was like, I gotta go back and double check that when I get there.
You mean you only go down to the surface?
So these are the spherical coordinates, right? And the spherical coordinates, theta goes from 0 to pi, and phi goes from 0 to 2 pi. Does that make sense?
Yeah.
But you don't radiate into the sun. So you only go down to here for this angle.
So you're just saying that we only see half of the sphere?
You only see the top half of the sky.
Yeah, okay. Yeah.
Yeah.
Okay, cool.
And because of the sine theta, this whole integral just works out to just be pi. There's a trig identity in there. I don't exactly remember off the top of my head how to do that integral, but it's a straightforward integral.
Like a half angle formula?
It's a half angle formula. Because I think this is sine 2 theta, and now I forget exactly how the geometry works on this integral.
What comes after the sine, cosine, theta?
D theta d phi. So it's just the little integrators that you need for the integral. Okay, so now here I've picked up. Oh, hey, what time is it?
208.
2:08. Okay. I'm going to do a U substitution in 2 minutes. So now I'm left with, so that thing just picks up a pi squared. So I'm left with 4 pi squared r squared b nu of t, because I haven't actually touched anything in the actual black body. All I've done is pick up a 4 pi squared. So now, here is the bit, here are the weeds that I always get stuck in when I'm trying to do math and tell a story at the same time. So we got to integrate lambda. That's the only variable that we have left. So we've integrated the area and we've integrated the solid angle. So the only thing that's left is wavelength, and then we have watts. So every time I do an integral, I lose a unit, right? So now we're just integrating over d lambda, and I've got 2hc squared lambda to the minus 5 over e to the h c over lambda kt minus 1. And I'm going to say that hc over lambda kt equals u. So this is just a u substitution like you've done in calculus. Hopefully you've done this a whole bunch of times. I'm going to do it really slow because if I don't really do it really slow, I screw it up. So Now I need to take a derivative of this, so I get hc over, I get a minus hc over lambda squared kt d lambda equals du. So I'm left with okay. I'm gonna, because time is running short, and this is where I always have to stare at it for like 5 minutes if I didn't practice it. All you do is finish up this u substitution. So you take u, here's u, you construct du just by taking an imaginary derivative. You take a derivative with respect to nothing of your u substitution. So that's why I get a lambda squared here, because 1 over lambda is lambda squared, and I get a du here because that's just du. So then we solve for lambda, and we plug back in here. So the denominator turns into e to the x minus 1, and the numerator turns into algebra. So you do some algebra to get a u in here, and you'll be left with a couple powers of u, and then they'll cancel out from that, and then this will be left, like, this will ultimately turn into a u cubed. Does that make sense? So the algebra will just cancel out, and you'll be left with x cubed over x dx, which you know, and then all of the leftover constants that you get from your u substitution. Does that make sense, at least in broad strokes? Because I'm out of time now. If you're super dying for it, I will do this slow when we start on Tuesday, but I'm gonna wrap it up from there. Not Tuesday, Wednesday.
I didn't know what questions to use on 3C and 3D. And I feel like it was easy because everything else wasn't to this point. I had to know what questions to use. I think you skipped that part.
Did I talk Oh, I totally skipped problem 3.
Yeah.
I'm sorry about that.
Come in like tomorrow if you have office hours.
No. I'll just show you how to do it because it's actually not all that hard. You just have to. It's a geometry problem. Sorry about that. I'm not sure how I skipped number 3.
That's why you
Okay, so you start with the luminosity from here. That compute as then you get the luminosity. Then you get the flux.
Did you saw you the other day? You were like looking down.
As the where D is 1 AU.
I don't know, she could say hi.
But that gives you the flux.
I just will be a little confused for a
So
second.
then what you need to do is compute the total power that the planet will
I
take.
like how this started as
Which is just
actually
the
like
flux
behind
times
your
the area.
little spray toy, and it's ended up as this.
And the area is not 4 pi r squared, it's just pi r squared. And then that's it for that. So the power here is that. And then if it's in equilibrium, it's absorbing the same. It's
Sorry, that was
it's
me.
radiating. And you plug it back into this will be the same as this if it's in equilibrium. So this is then
The power is equal to the luminosity.
power is going to be the luminosity in equilibrium. So if it's absorbing the same as it's radiating, then this is the same as another area sigma t to the 4. Yeah, if you want to just go ahead.
And then if I'm good.
Yeah, just do it.
Especially 4 because I didn't get any of that.
Okay.
But I paid attention in class. I it's okay.
Yeah, go ahead. I have a great idea. It's good. Just go ahead.
Are you going now?
That's the question.
Yeah, I also had some problems with for this distance, knowledge.
Are we gonna start?
I don't know how you
Ow,
do
that kind of hurt.
Where
I
at?
think that might do
It was,
Where'd I get
It's
something?
126 parsecs or something like that.
I'll do that. I'll do
I
that.
think it's
I like scraps, like half a dozen.
Two.
Oh, I'll put my backpack up for one.
number 6.
Yeah, so here, D is 10, the little m minus big M over 5 plus 1. And that's it.
And it's just plug and play.
Yeah.
This, I think he's outside now.
Why is it over 5?
So the distance modulus is little m minus big M, right? And this is 5 times the log base 10 of the distance over 10 parsecs.
Okay.
Hi, you gave it
out.
I just feel like
Well, it was
so
a
for the
different point. It was like a nice little circle that
but
you
for some
could
of them I
like
wasn't sure.
spin around.
I didn't even have the notes were posted, so I was just
Like
going with
this.
The lectures, the slides are,
Right,
not all the notes always are.
Okay, because I was looking at it, that was there, so I like had to like look up stuff. So I was watching
Well, at
videos,
first it
and
was
so
stretch out on one
first
side,
I
and then it
I
annoyed me,
used,
and then I
like,
figured out I could
you
stretch
know
out
what
the rest of it.
lines
And
have
that
to
was
do, how to figure out
stretched
something.
out.
So
So I'm
one time my number is like kind of close to what you got, but sometimes a little different.
I don't care about
Now I can wear it.
Okay.
So as long as
What
the
is
process
what
is,
is the process is weird.
which one?
It's geez, the one that
Yeah, I can
gives you
find
like
it like anywhere in my
up on it.
notes,
But
like the
I-
velocity of.
it was.
It's like makeup, right?
That's
The way I
For,
did
you know,
it
when you
was-
do the log
I
of
had to get
L
the
over L
notes were
naught,
posted, so
the
I'm
L
sorry.
naught is beta, that's the luminosity.
So
It
good.
is.
Yeah, I couldn't
posted
find it
spot.
anywhere. I think I accidentally forgot that and used the sun's luminosity.
There's a, yeah, it's only on the textbook that uses the sun's velocity and then it's that velocity.
It's the
That's
one
probably
that's, like,
simple,
way
that's like, I know that's like the sun symbol, so I was like,
Oh, number 6.
Yes.
See, it's still fun, even
Wait,
though
wait,
it's
hold on.
entirely. Oh, aha! Where did it go? Oh, you got one dress.
And then a raise 2.5.
Oh, now it says fail to download resources.
I
Guess
just
what?
was that next
I was
to
literally
Steve.
playing up.
Mine's easy.
Do the math and think about it.
Okay, because I was like,
Look at the distance modulus definition.
Wow.
See how to get it.
Once
So
he wrote it
distance
down,
modulus
I
for
would've been-
spin.
I would not have remembered it on my own.
Okay.
Undo that. How do you undo that?
To
So
get
let's,
this.
yeah, get D. Don't look at your phone anymore.
Oh, no, no.
How do you get D from this?
Divide this by 5.
Uh-huh.
E both sides.
Oh, no.
Having used Taylor
Man
series,
has
I
scratched on
used Taylor series so much when I was taking
I wonder if everyone is doing stuff.
No, I got selected. I hated
No.
the rest.
This is the second time this month.
No.
Man is sick.
Like what?
Almost.
Like,
You just messed up the log. So this is log base 10.
What about the Venus character? They're like, the sum is 7 times x.
I can take,
not 7 times x to the power.
So if I raise this
See,
to
I
10,
think I got it.
then that undoes the log. If I raise it to E, then I get E to the log base 10 of.
So only works for iron. Okay.
So it's gotta, you gotta undo it with whatever is in the base, or change base,
I could probably do it right now.
Okay.
but,
So do
So
I
far,
raise
ODU
that
has
like
been
the power
pretty chill.
of
It's just-
yeah, so,
It's easy,
when
but
you're
at the same
undoing
time,
this,
it's like a lot of memorization.
it's just mu over
I like
5
just
Oh, back
doing
to
the math.
school.
I don't like having to memorize stuff.
log of D, so I raise both sides to 10.
I
haven't heard from them.
Oh,
And then
okay.
times that by
Yeah.
10.
And this is in 10 parsecs, so if you want an
I
answer,
kinda
I'm just gonna
got
go
it.
through and bring you like all
Parsecs by
problems, all
10,
questions.
like,
I don't care how long it is.
yeah. The only
I'm
thing you
doing
messed
that
up
like
with
every
is
class. Like I'm doing that
Yeah,
with this
okay.
class, I'm doing that with PBS.
I
PBS
don't know,
is just
I've been watching like the YouTube, like online astro professor, whatever.
We don't have a mentor, guys.
Yeah, that's all right.
That was a weird
I
Oh,
just like
Yeah.
graph a lot.
That's fine. I like to save a bunch of